Okay, a word problem where we're trying to optimize our revenue. So a concert promoter has found that if she sells tickets for $50 each, she can sell 1,200 tickets. But for each $5 she raises the price, 50 less people attend. 50 less tickets are sold. So at what price should she sell the tickets at to maximize her revenue? All right, so our goal here is to maximize the revenue. And our revenue can be calculated as all the money we bring in, right? So sometimes we think of that as the price we're going to charge multiplied by however many tickets we sell. We usually call that the quantity. Or with variables, a lot of times P for price and Q for quantity is going to represent our revenue. But as you can see over here, we have two variables over on the right-hand side, and that's a little bit of a problem. So let's delve back into that price and number of tickets. So how they kind of describe this, for whatever price we charge, we get a certain quantity coming out. All right, so I like to think of this as P is our input value and Q is our output value. So let's set these up as ordered pairs. I like to think of that as if we were charging $50 for a price, we would sell 1,200 tickets. But if we raise our prices by $5, so go up to say $55, we're going to have 50 less people attend. So it'd be like 1,150 tickets sold. Or if we did it again, we would be charging $60 and only 1,100 people would attend. Well, because this, for every $5 we raise our prices, the exact same number of people would not show up for the thing, we can think of this as being a linear relationship, connecting together our price and our quantity. Sometimes we call that the demand function. All right, a demand function connects together price and quantity every single time. All right, so a linear function would look like this, where we have Q, our output value, equals M times P plus B, where M is the slope of our line, the linear function, and B would be the y-intercept. So to get to this function, what we want to do first is probably calculate what is our slope of this line going to be. Well, I've written out some ordered pairs over there on the left-hand side. I'm going to choose to go with 1,100, that y value, or q value, minus 1,200, over 60 minus 50, to see the rate of change here. All right, so that's going to be negative 100 over 10, works out to be negative 10 for our value for m. So at this point, our function looks like this. Q equals negative 10 multiplied by P plus B. All right, we still don't know our y-intercept B. So to find that y-intercept, what I'm going to suggest is we fill in one of these ordered pairs for our P and for our Q. In this one, I'm going to elect to choose the first one that we were given there, where 1,200 gets filled in for our Q. Then we have negative 10 multiplied by 50 gets filled in for our P value, plus B. Bringing this work down this direction, this will be 1,200 equals negative 500 plus B. By adding 500 to the other side, we're going to have 1,700 for our value for B. All right, so now our demand function can be represented by Q equals negative 10 times whatever our price we're charging plus 1,700. All right, this is going to be important to use this demand function. And remember, our goal on this is over there with the revenue function. The revenue function we want in terms of only a single variable. So in our case, what I'm going to do is I'm going to replace Q over on the right-hand side, the quantity, with negative 10 P plus 1,700 directly from what we just calculated over here on the left-hand side. All right, now those are multiplied together. So let's go ahead and distribute the P. So negative 10 P squared plus 1,700 P. Now our revenue function is only in terms of a single variable, so we can go ahead and try to find our critical values by taking the derivative, using the power rule here. So negative 20 P plus 1,700. And what we'd like to do is figure out critical value, so that's whenever this is equal to 0. So I'm going to set that equal to 0 and work on solving down. So negative 20p, and we're going to subtract the 1,700, move it to the other side, and divide both sides by negative 20. So this will give us an ideal price, P, of $85. Okay, that answers our question. We were looking for at what price should we sell the tickets at to maximize our revenue. We could figure out our maximum revenue by plugging into the revenue function before we took the derivative. Hope this helps out as you're working on these. We could also verify that this is indeed where we get a maximum. Although in looking at our revenue function, this revenue function is going to be a parabola, right? A quadratic that's been flipped upside down. So that highest point is going to be at the very, very top of this. We could do the second derivative test if we wanted to. Our double prime would be -20. And that's always negative, indicating concave down. Concave down everywhere, which we can kind of see from that graph up there, which indicates that we're going to have a maximum at that value of P. All right, hope this helps out. Good luck on maximizing revenue.